Okay, so what we've seen in that example then is we focus very much on the ways of defining a function over lists using pattern matching. And we've seen these various kinds of patterns that you might use. And of these, the most important ones, the ones we're going to use much more when defining functions from scratch, will be the empty list pattern and the non-empty list pattern. So those two will be the key here. And to see those really working in action, we're going to look at some functions over lists, some slightly less trivial ones than this one, which we're going to define by recursion. And we'll start by looking at the length of a list. And this is a standard function. So for example, if we had list 1, that's that list there, the length of that list is 5. There are 5 things in that list. Even though some of the things themselves in the list have a different size, length calculates simply the number of things in the list. So let's define that. I'm going to call it len. And we're going to define it by defining it in 2 cases. And this is typical for a recursive function. It's going to be very typical for a recursive function over lists. We're going to define the 2 cases as when we have a list that is empty or a list that is non-empty. So they're the 2 cases that we're going to define in our definition for the length function. And this covers all possible lists. Every list is either an empty list or it's a non-empty list that starts with some element x, and this is the rest of the list. And this is a typical naming convention. If we're going to call the element x, we don't know what it is, what kind, we don't even know what type it is. It could be any type. But there's one of them called x, and this is going to be a list of many x's. So we use the plural here, x and x's. Okay, what's the length of the empty list? How many things are there in the empty list? There are none. So that's going to be the base case of our recursion. And now let's move over to the recursive case. And what we're going to do in this example is work out the length of this list, this non-empty list, in terms of the length of the sublist. So let's assume that we know how big x's is. Let's assume we know the answer to that. How do we work out the answer for this? Well, what's the relationship between the length of this list and the length of this list? It's easy because this list is just one element longer. So this length is one element shorter. And so we just add 1 to that to calculate the length of this. So this is a recursive definition of the length function, which computes the length by kind of counting 1 for every element that it finds in the lists. And when it finally gets down to the empty list, it returns 0. Okay, let's take one more example. And that's example of the last function that we gave in the that we used in the previous example. And we're going to use the same pattern here, the last of the empty and the last of the non-empty list. And we think of this as the base case here. So what is the base case of last? What is the last element of the empty list? Could it be the empty list maybe? Well, actually no. The type of the last function is the same as the type of the elements in the list. So for example here, the last of the rest of this list was a string. We took a list of strings and the last element should be a single string. So the last element, the type of the last element is not necessarily a list. It's the same as the type of the things in the list. So the last element of the empty list cannot be the empty list. Because, so what is it? What does last empty give us? Well, it gives us an error. So in fact, this is not the base case. This is not the simplest case for the last function. This is the error case. So so what is the base case then? The base case for the last function is actually a list with only one element in it. That's the simplest non-error case that we can have. And how do we write a list with exactly one element? Well, we use the square brackets notation. That's the list with exactly one element. And what is the last element of that list that only has one element? Well, it must be that element. Okay, so now we can come on to the recursive case. Now we know we have a list that is not empty and doesn't have one element. It has one element followed by at least one more element. So what is the last element? How do we compute the last element of this? We're going to use the same recursive idea. We're going to try and compute it in terms of the last element of this smaller list. So if we know the last element of this smaller list, how do we compute the last element of this bigger list? Well, let's take an example. Let's suppose we want to compute the last element of the list 1, 2, and 3. But we want to do it by using the last element of the shorter list, 2, 3. Well, as you see, they're in fact the same thing. If we knew how to compute the last element of 2, 3, then we know how to compute the last element of any list that ends with 2, 3, including this one here. So in fact, this is the solution. The last element of this bigger list is the last element of this slightly smaller one. And eventually, we will get down to the base case, which is the list with just a single element. And that will be, by default, the last element. Okay, before we finish here, let's think about putting some types in for these functions. And I'm going to start with the last function. So I'll rename this so that I don't get name clashes with the prelude. But we can ask Haskell, what do you think the type of last prime is? And it will tell us. And what it's telling us is that it works for a list of p's. Well, what is p? What is p here? P isn't a type. P is a type variable, a small letter, something with a small letter. Remember, the types that we know about, like bool, for example, will begin with a capital letter. But the type here, p, is a small letter, and that means it's a type variable. It means that it's a standing for any type you like. So this function last, it works for a list of integers. Yep. It works for a list of bools. It works for a list of anything you like. There are an infinite number of types that it will work for. But the only thing we do know is that whatever type the elements have in the list you give it, that will be the type of the result. So if you give it a list of integers, you'll get back an integer. If you give it a list of bools, you'll get back a bool, and so on. And the way that's represented is by a so-called polymorphic type, what you would call in Java speak a generic type. So this is a generic function. In Haskell speak, we say polymorphic function because we like to be fancy. Okay, so the type of last, I can put it in. It takes a list of, I'm not going to call it P, why did I not want to call it? I'm going to call it a list of A. It's the same thing. It's just the name of a variable. It doesn't matter what we call it. So you take a list of anything A, and it gives you back one of those A's, the very last one in that list. So what about the type of length of len then? So then you might expect that the len function is going to take also a list of anything you like. It doesn't matter what's in the list. What you're going to get as a result is some kind of number. Well, what kind of number is it? Well, we could choose if we're going to give it our own type. We could give it the type int, for example. And why would we do that? Well, actually, that's the type that the... I say that, I better check what the type of length is, the standard length function. Well, you see, we get caught out because Haskell will always come up with the most general type for a given definition. And that general type may be more general than we expected. And in this case, it works not only for lists of things, but any other kind of collection which has this so-called foldable property that you can fold together, combining the elements. So the type of length as it's given in the prelude is a bit too general for us to kind of get our heads around just at the moment. So we're not going to worry too much about it, other than to say that it works perfectly fine for lists of things. We can take the length of a list of things, and it works as you would expect. But it also works on other types of collections, and it gives an int. And that's because when we're building data structures, we're not going to expect those data structures to get so big, things like lists, that an int wouldn't be big enough to count the elements in it. And we're not going to build something with 2 to the power something elements, 2 to the 100 elements, because that's going to be too big. So int is perfectly fine for that. But actually, little experiment here. What actually does Haskell say? What does Haskell infer for the type of len? And again, we'll get something different. Different again. Let me reload the file and ask about the type of len. And now we get something different again. It's saying, well, it does, my definition only works for lists. The Prelude definition works for other things. My definition only works for lists because I built it using nil and the cons operation, and they're the list constructors. But the result type is a type P. What is P? Well, it's not any type you like. It's any kind of number you like. So if we let Haskell infer the type, it will say this is a function that takes a list of things and returns a number. What kind of number? Well, whichever number you want. If you wanted an int, then well, it'll be an int. If you wanted a double, then this could be a double. So this is something called overloading. It's another kind of polymorphism, but a different kind. And this num is a type class. It refers to a whole gang of types, the gang of number types, including integer, int, double, and float, and maybe other ones too. We're not going to get too much into this for now, but just so you know, when you look at types, the types you see may be more complex than you're expecting. And that's another reason why you may simplify your life when you only want a simple type. For example, in this case, I maybe only want something which takes a list of things and returns an int. Then by declaring that, then we keep life simple. The error messages we get for types will be also somewhat simpler.